Hello, students. We're going to talk about amino acids forming peptide linkages. This is one of the most famous types of bonds in biochemistry. So, proteins will be formed when amino acids come together. And what will happen is the carboxyl group will react with the amino group, and in the process, form water. So, it's going to release water. And then you'll form the peptide bond, which is shown here. And we're going to practice drawing these. I think they make a little more sense when we start drawing them out. Now, one of the things I want you to notice about this diagram is it's a really pretty picture, but once again, like I was telling you, that there's a little bit of an inconsistency here because remember the amino group would be protonated at pH 7.4. The carboxylate group would be deprotonated. Part of the reason why this diagram is shown this way is to make more sense out of the fact that water comes out. So if we look at H2, 1H2O, right, here's the water, it comes off, then you can see where the bond would form with the NH group. Okay, but we're still going to practice drawing them more in just a moment. The N-terminus is where the amino group is, and the C-terminus is the carboxy terminus with the COO minus. Okay, so here's a little bit better one. I like this one because it shows it correctly. So you see how the carboxyl terminus or C-terminus here is deprotonated, which we would expect at pH 7.4, and then the amino terminus is or N-terminus is protonated based on its pKa. Okay, so all of these take a second to identify where the peptide linkages are. So you can pause me. The peptide linkage is here, right? Is here, is here, is here. Okay, so that has the amide bonds. Remember, amide is that organic functional group, C double bond ON. Okay, and now there's rotation here at the alpha carbons. So that's alpha carbons. So there is rotation around those alpha carbons, meaning that, yes, it's tetrahedral, but they can rotate, which is why do you see how the R group can be on opposite sides of this particular chain. Also, it has a three-dimensional structure to it, tetrahedral around the alpha carbons. Now, the one thing that come up a little bit later in a slide, but I might as well mention it now because I normally do anyways. And I'm going to erase that red that I just put in there. Okay, yeah, it looks better without that. So these nitrogens here have lone pairs. They're normally not drawn in, they're implied. But one of the important things is that what will happen is that there is resonance in that amide linkage. So drawing it here, there's resonance. Do you recall resonance is where electron density is moved or pushed? So that essentially what I'm saying with this drawing is that there is a double bond nature to that amide linkage. It's not fully double bond. Remember, resonance is sort of that delocalized electrons. And so what will happen then is that within the amide linkage, there is no rotation around that bond. It stays as a plane. And we'll see some pictures of that in a few minutes. Okay, oligopeptide means that you have peptide chains of a few residues, and polypeptides contain 15 to 20 residues. Okay, now the word residues starts to pop into play. Residues is another way of saying amino acids. Okay, so that word is something that we're just going to put into our vocabulary right now. Okay, now the way that we write these will always be listed from N terminus. So always N terminus to C terminus. And then here we have the peptide linkages or peptides. So we have tyrosine, glycine, phenylalanine, leucine. Okay, so those also, as shown, these aren't as controversial as in terms of their acidity, basicity. So these guys are shown at physiological pH. So if you invest your time that you need to invest on figuring out what charges the R groups have at pH 7.4, then that plays a role here. So let's take tyrosine for a moment. Tyrosine has an R group pKa of 10.33. So at pH 7.4, that is not deprotonated. So we would draw that with the OH. And then the rest of them don't have that discussion because they don't have an R group that has a pKa listed because they don't have that acidic quality to them. Okay, but when we go to draw these, the best thing to do is to kind of do a little bit of a shortcut where the backbone, I'm going to highlight it, N, C, C double bond O, 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 N, C, C double bond O. So do you notice that that's our backbone, and sticking off of that backbone are the R groups, R1, R2, R3, R4, R5. Now, if when you guys draw yours, I'm not as picky about drawing them with their tetrahedral shape, but I think it's very important to understand that it has those because that's how these proteins are going to get their 3D structure. Most proteins have between 50 and 2,000 amino acids, and the average mass of an amino acid just averages 110. So, most proteins have a molar mass of 550 to 220,000. So some can be very large. The mass unit that's used a lot in biochemistry is Daltons. I don't ask you that as a question, but just so you're aware, if you ever see them with that unit, it's referencing their mass. Okay, so here's a very simple structure: serine, glycine, tyrosine, alanine, and leucine. Okay, so I'm going to go ahead and I'm going to switch to this one where let's go ahead and draw out a structure of amino acids. Let's see. I think we can pick, let's do serine. Oops, let me get my pen back. Serine, alanine, aspartate. Let's just start with that. Boy, that's a depressing one, but sorry on that. Okay, so this is what we're going to do. We're going to draw always the backbone first. Now, I know water's coming out of this, but if you try to always draw them showing that water coming out, it can be enormously confusing and you can get the wrong structure. So we're going to do N, C, C double bond O. N, C, C double bond O, N, C, C double bond O. So that's our backbone. Start with your backbone, always. Okay, and then what we're going to do is we're going to fill things in. So here at the end, we would fill in the NH3 plus, and we know that that's protonated because the pKa's are all around 9.6-ish. Okay, and so at pH 7.4, then we know that that's protonated. We also know that over on this other end, at pKa is around 2, correct? So that would be deprotonated at 7.4. Okay, so pause me a second and go ahead and fill in your R groups on the alpha carbon. Okay, go ahead and fill in your R groups. You can pause me. Okay, so here's the thing is that now you're going to do serine, right? Going to draw it as CH2OH. Now I have to check my pKa values and make sure that it doesn't have a pKr, which it doesn't. So that stays like that. Okay, that does not have a pKa for the R group. Then I'm going to draw the H on here. Okay, next we go to the alanine. Okay, and then our last one is aspartate. Now aspartic acid, CH2COOH. But now I'm going to look up that pKa, and that pKa for aspartic acid is 3.86. And so that means that I have to adjust that, right? That is deprotonated at physiological pH. And so I'm going to draw that correctly. Finishing up the structure, this has a hydrogen, the nitrogens have hydrogens, and then I'm done. Okay, now, if you look at the previous pictures, if you want to really draw it even a little bit better, you can do the alternating. You know where they're alternating from each other? The R's were going in different directions. So that's fine. Sometimes students like drawing it that way. You know, where they showed R1 over here and then R2 over there and then R3 over on this side again. So I can show you that going back. You see how this one has all the R groups on the same side, but the other one was what I was going to tell you here is that they tend to like to draw them this way. There are R1s on this side, R1s on this side, and then the C double bond O are alternating sides as well. Lastly, if you prefer, go ahead and draw them with the line, right? The line structures. Completely fine if you prefer it. I choose not to, only because I think for teaching purposes, the lines can throw students off. So, but if many of you probably learned them with the line or prefer that, and that is totally fine. Here's a good picture of the resonance structure. So here's the nitrogen with the lone pairs, and it forms a double bonded partially. Now this is partial, delocalized. So the electrons don't lie only in between the C and the O. There's this partial double bond character to N. And what that does is it creates a plane that those guys have to stay together. So these guys have to stay together. And that's what this blue part of this diagram is saying. So there's rotation here and here, but there's not rotation between here and here. That's has that partially double bond nature. Okay. So keeping that in mind, then see these green planes. That's where you have that rigidity there between in the amide linkage. And then you can see, though, that the R groups extend above and below those particular bonds, the planes of the amide bond. Okay. Peptides tend to be stable unless there's a strong acid or a catalyst present. At high acid concentrations, and also temperature tend to degrade proteins into free amino acids. And then there's special enzymes that'll cleave peptide bonds. And we're going to talk about them in great detail in chapter 7. Proteins and sequences are determined in lab through something called Edmond degradation. Because we don't have a lab that's associated with this class. I do not do too many of those procedures. Just every once in a while, we'll talk about how we will isolate certain amino acids, but I don't spend too much time on that chapter and the information regarding laboratory work. Okay, and this has just some information. We will come back to this because we actually study this one called chymotrypsin in a lot of detail. That's an enzyme that will cleave the peptide chain. It's found in our digestive tract, and it prefers to slice them where there is aromatic amino acids. So that's its preference. The leucine isn't, but the other three are aromatic. So that's kind of its preferred site. Okay, so the two basic possible configurations, if we think of that amide linkage as having a possible or partial double bond, then peptides can exist as cis and trans. So this is showing here where they tend to be trans to one another. If you look sterically, that kind of helps them to give them a little bit more space. Okay, naming peptides, starting at the N-terminus, we either use the 3-letter code abbreviation, or for longer peptides, you can use the 1-letter abbreviations. And in the worksheet number 2, you're going to practice drawing these out. Okay, and remember what you have to do: draw the backbone, fill in your R groups, but then you have to look to see what's the correct way of writing the R group at pH 7.4.